Essentially, this workshop for today contains two topics. One is on topic modeling, an unsupervised approach. And the second session, which Pratiti will take, it will be on the bouquet of services and tools that IBM Watson provides to enable all the things that we have talked about since yesterday and I will be talking about today. Um, so let me start sharing my screen. Can you guys see my screen? Just give me a thumbs up, right, as an indication that you can.
Yes, we do.
Good. Okay. Um, I I would like the session to be interactive, and I strongly urge people to ask questions. When I am presenting, I cannot look at the chat window, the question that comes. If you will ask questions, then most likely the same questions other participants could also have. I mean, it's a common phenomenon, right? The questions that may come to my mind are the same set of questions that may be arising in other people's mind. And in the online sessions, it becomes more important actually, to ask questions so that the speaker does not feel that he's the only one he's talking to a computer. Nobody wants to talk to a computer. Before I begin this presentation, let me introduce myself, and I am Harshit Kumar. I am a senior member of technical staff at IBM Research, and I have been working on two things in the past, two broad things. One is conversational AI, and the second is AIOPs. And we have been extensively using ML and AI and stats um, in, at least I can say, for both the products that we have built at IBM Research. The first thing is there is this repository that Dipanjana created for all of us. And in that repository, there are two files here. One is a PPT, which I'm using today for presentation. And the second one is a notebook that we will be using for the hands-on session. And then there is this file readme.md. It contains one additional step. So assuming that you have already followed all these steps after doing all the installation requirements.txt, now you need to do one more step while you are in your Python environment tutorial. What does that mean? Remember here, we created this activated the environment tutorial. While you are in this environment tutorial, you have to type this command on your terminal, python 3-m space e download en. What it does is it installs a set of packages. Spacey is an NLP library. It installs a set of English language packages that we will be using in our this notebook, topic modeling LDA.pptx. And please, while I'm presenting, use the time to make sure that uh, this step has been executed, and you can then open this uh, notebook, which looks something like this, um, right? And then execute the first one, right? The first cell. If first cell executes, perfectly without any error, then most likely 99% of uh, the rest of the cells will also execute. So it contains all the packages that are required. And I'm going to use a lot of packages um, for the hands-on session. So let's get back to the PPT now. And as again, right, I prefer the session to be, not prefer, I want it to be interactive, to be honest. So yesterday we had introduction to some statistics and basic fundamentals of machine learning. And Debanjana talked about supervised learning algorithms. She talked about deep learning supervised algorithms. I am going to talk about the unsupervised learning algorithm. Only one. But first, let's understand why do we have two classes of algorithms? One is supervised and one is unsupervised. We use supervised algorithms when, for a given data set, we have the labels available. Labels means the annotation, the task that we want to do. When there are no labels, which is most likely the case, somebody will provide you data set without any labels. And then there comes the unsupervised learning algorithms. And mostly unsupervised learning algorithms, they are into two buckets. I can either do clustering with them, or I can extract latent variables. Latent means it's hidden. It's not as apparent, as visible as other information. It's a hidden information, right? And we will see what that hidden information is. And we will be talking about topic modeling. And let's just now go to the definition of topic modeling. So what is topic modeling? Um, Basically, topic modeling is saying that I have a bunch of documents, news articles or uh, research papers. I want to arrange them or categorize them by topics. So I could have a bunch of documents belonging to topic one. I could have another bunch of documents belonging to topic two. And I could have another bunch of documents belonging to topic three, and so on, right? But the problem is, nobody tells me in the beginning what are the topics. Take an example. Let's say I throw in 100 news articles and I ask somebody, can you group the articles that are very similar to each other into groups? So make as many groups as you want. You decide the name of the group. You decide which article goes into which group. It's a challenging task. You look at the first article, well, this one looks like politics. Let me put that into politics. You look at the second article, this looks like to me science. Put that into the science group. You look at the third article, you see that this looks like maybe sports, goes into the sports category. And it may also happen that there are certain topics that may belong to more than one topic, and that's where the challenge comes. Whether it is politics or whether it is uh, maybe, say, for example, satire, right? There are some satire political jokes, right? It could be a satire topic also, not a truly political article. So there is a hidden thematic structure, inside each document, which we human beings can read and figure out. And we want the machine to do the same thing using topic modeling, right? So the algorithm that comes under topic modeling, it helps us to summarize basically, right? Large document collections. And it, in a way now, if I can group my news articles into these topics, each document going to one topic, I am essentially annotating them. right? I am giving uh, an article a label of news, another article I am giving a label of sports, and so on, right? So it allows us to annotate large volumes of unlabeled text. And then what is a topic? A topic consists of a cluster of words, right? It's a cluster of words that homogeneous words, not just any words, homogeneous words, right? For example, in a sports topic, I may have words like in the articles, obviously. In the articles, I may have words like cricket, century, ball, soccer, hockey, and so on, right? But here we need to understand the difference between clustering and topic modeling. There is a subtle difference. Clustering is not latent, whereas topic modeling is based on latent information. So clustering is based on the uh, words that are present in the document, whereas topic modeling is based on the abstract topics. I am taking a simple example, sports. I could define two topics, sports cricket and sports soccer, right? What level of granularity I want that I can define, I can let my algorithm figure out. There is no way to tell the algorithm that make a topic for sports cricket and make a topic for sports soccer, right? But I can tune some parameter and let my algorithm figure out how many topics it wants. Essentially, at a higher level, it's a hidden thematic structure consisting of latent variables. So I won't go into clustering much, but these are some of the high level clustering algorithms. Um, there's a hard clustering, there's a hierarchy clustering, and there's a soft fuzzy clustering. Now let's come to topic modeling. So I have a data set on the left hand side, collection of text documents, and in this is my sum, the black one is my sum algorithm, right? Some model that I am building, right? This part that I am building, which should essentially be able to uh, categorize these documents into topics. So this is each circle that you see here is a collection of documents that are belonging to a particular topic. So here I'm showing three such topics, right? And each topic is a cluster of words, as I said. And within each topic, this is important, right? In each topic, when I have the documents, I can also see the word distribution. There may be a word, maybe let's say the topic is soccer, right? Then uh, there may be a word which is, say, for example, here, Manchester United, right? There may be a word here which is FIFA, right? So what I will have is finally um, a word distribution also for each topic, right? Word distribution means how the words are distributed in a topic. And then for each document, I could have a distribution of topic. Like I said, one topic could belong to, sorry, one document could belong to multiple topics. Any questions for me here? Well, if there are no questions, I will finish early. Mind, remember that, right? Because I lose interest. I feel like I'm talking to a computer. So I strongly encourage you to ask questions. Either I am doing a really good job that there are no questions, or I am doing a really bad job that nobody wants to ask questions. So here is a problem. I have this set of documents and I want to tell which topic does each document belong to. And for that, obviously, I need to know the content of these documents. Right? And I have 4 topics, say for example, politics, science, cinema, and sports. So I want to figure out what document does each topic belongs to. I mean, I want to put a label for each document. Say for example, Kohli, this first document contains these words. Kohli inaugurate Nike shoes. So what do you think?
So Harshit, there is a question. Saida, can you speak up? If you can
Yeah,
just.
please speak up. Please speak up, right? Yeah.
Sir, good morning, sir. So
Yeah.
what is the clustering criteria, sir?
Clustering, I never talked about clustering criteria, did I?
No, sir, you spoke only about clustering.
Yes. There is nothing like clustering criteria. Let me go back. Where do you see the word clustering criteria?
No, sir, you said that clustering is divided into three, and again, it is hard clustering, fuzzy, and hierarchical.
Right, right.
So based on what would you say that this data requires hard clustering or this data requires hierarchical clustering? Based on what criteria would you decide this, sir?
There are no golden rules to answer that question actually, Um, what one way is you look at your data, and how do you look at your data, right? You have to look at your data on an XY axis. And if you see clearly separable groups, then use hard clustering. If you see lots of overlaps between the groups of documents, then you use hierarchical clustering or soft fuzzy clustering, right? So soft or fuzzy clustering allows you to have soft boundaries that you can play around with. Hierarchical clustering allows you to build uh, hierarchies of cluster. Say, for example, one big cluster could have two, let's say this is one cluster, and there is a document one, document two, but there is another small cluster within it, which contains maybe, let's say, 4 documents. There is another cluster within this big cluster, which contains 3 documents. So hierarchical clustering gives you both a low granularity and a high granularity, which hard clustering won't be able to do. Hard clustering will give you just clearly separable clusters, just like this. And each one will contain some points. What hierarchical will do, it may say, hey, these two can also be grouped together into one bigger cluster, and these two can also be grouped together into one bigger cluster. This is my hierarchical clustering following, right? But there is no such criteria for clustering. These things are all based on, you use some intuition, you do some experiments, you go back and forth, you try different parameters, and you look at your clusters, and then you say, hey, these clusters look good to me. And there are some metrics also like purity, entropy, NMI, VI, ARI. These are all the metrics that we use for evaluating how good the clusters are. But remember, clustering is you never have label data. You never know at the beginning what are good clusters and what are bad clusters. So these are difficult problems because you never know what are good and bad clusters. Have I answered your question, Saida?
Thank you, sir. Actually, this doubt arises because initially we are unaware of the data itself, the
Yes,
label of the data itself. Then,
right.
without knowing what is the data, knowing if the data is going to be a subset or a superset of the data itself, or a hierarchy can be created,
Uh-huh.
or boundaries will exist.
Uh-huh.
Initially, it is very difficult to even interpret, no, sir.
No, you can always plot your data on a two-dimension axis. And I will show you that in my hands-on demos. You can plot your data on a two-dimension axis. See, think about it like this. I can have a XY axis and I can say here is document 1, here is document 2, here is document 3, here is document 4, document 5, document 6. And it may happen, I may have document 7, 8, 9, 10, 11, 12 here. Now when somebody look at this, anybody who look at this can tell that, well, there are two clusters. This is the first cluster and this is the second cluster. Obviously, this may not be 100% correct, but plotting your data once on an XY axis gives you some intuition. How many groups are here, right? There are no labels, right? I am just plotting them on an XY axis. Does it make sense?
Yes, sir. Thank you, sir.
Okay. Yes, so I was talking about this part. So if first article is of Kohli inaugurating Nike shoes, what topic would you like to associate it with? Anybody?
Sports.
Good. I deliberately did this, I am not going to move if nobody gives me answer. The second one, throw ball velocity break class. Which topic does it belong to?
Science.
Science.
Throw ball velocity break class. Yes, there's a ball here, but see, human being can tell. Okay, I have sports. Sports is SP and science is SC. So this is SP and the second one is SC. The third one, release science fiction matrix. There's a matrix, there's a release science fiction. Which topic is it?
Cinema.
Cinema.
Cinema. Yes. This is not science, right? Although it contains word like matrix, science, but because there is a word release here, somebody thinks, well, matrix is the name of a movie. White screen find area perimeter.
Science.
Science. White screen IPL match.
Sports.
This is an easy. This is an easy one, sports, right? Election speech.
Politics.
Politics. But here, think about it, right? Somebody who hasn't watched a movie Matrix, he may be inclined towards thinking, this could be, maybe this is 80% cinema, maybe at least 10-20% I can call it, science. 10 to 20%, let me say. This one is also, I can say 95% science, but I may say that maybe it's a ball, velocity, you throw, there's a ball word here, right? And throw also, throw a ball, right? I would say sports maybe 5%. This is the distribution I was talking about in the previous slide, remember? The frequency distribution of words tells you what the topic is. Okay, so now that I know what each document is into which topic, see, this is what human has done, right? We want machine to do the same thing. So for that, we use an algorithm called as topic modeling, LDA. LDA is latent Dirichlet analysis. Latent word I am saying because the topics are hidden. Remember here, I told you that there are 4 topics: politics, sports, cinema, and science. But in true sense, we never know what the topics are, right? Remember that. It may be, this would be just a bunch of words. This would also be a bunch of words. This would be a bunch of words. And this will be also a bunch of words. And I will look at those bunch of words and say, hey, this looks to me like a topic cinema. So my model will figure out what are the bunch of words for each of the 4 topics and then associate document to those bunch of words. Okay, so if I just go forward, Kohli inaugurating Nike shoes goes to sports. White screen IPL match. Well, it's between sports and cinema, right? Because there is a white screen. It gives you some cinema angle also into it, right? Because generally IPL matches are screened on white screens, right? Release, science fiction, matrix. This is definitely cinema. Remember, I am putting this document here, not at the corners. What does that mean? Why is this document somewhere in the, not in the middle, but closer to sports, far away from cinema? Anybody can tell me what does it mean? Oh, this is an easy question according to me.
It is
Yeah,
more
go on.
likely to be sports than cinema,
Correct.
but there is at least a little chance of it being cinema. That's why it's not exactly at sports.
Right, right, right. So this is more likely to be sports than cinema. Thanks. And election speech goes into politics. Any document that talks about election and speech goes into politics. And a document that talks about throw, ball, velocity, break, glass goes into science. White screen, find area, parameter also goes into science. I would like this one to be maybe here. Right. So now I'm thinking about it. Right. There's a word white screen. Some, angle of cinema is there, right? Find area parameter is telling me it is related to science. So, and there is a reason why I am giving this geometrical shape here, which is a tetrahedron, right? So if I look at this, it's a tetrahedron, right? Because I think there are 4 topics and latent Dirichlet analysis geometrically tries to draw a distribution in a tetrahedron. And let's try to understand it in the analogy that will come in the next slide. Okay, let's say, Dibakar, please ask question. I cannot read the full sentence. I could see that you asked something, but the sentence didn't show me completely here on the screen. Can you please ask the question? Dibakar, I'm waiting for you. This is yeah, Dibakar, please.
Yeah, are you able to hear me?
Sorry?
Are you able to hear me?
Yes, I can hear you.
Okay. So my question is that is cement meaning of the words. I mean, how would it be understood without any labels or categories or something like that?
Your voice was breaking, so let me go back and see. How is the semantic meaning of words would be understood without the labels? Good question. Okay. This is the question, right?
Yes, yes.
From the contents of the documents. I have the documents and each document contains some words. From those words, I will be able to understand the semantic meaning of a document. Does it make sense?
Not clear. And how would unless you train it and say that this means this category,
Yes.
how would it say that it belongs to this topic?
Because I have in a document, there are words that belong to the category sports. Oh, it won't tell, as I said, it won't tell what the category is. It does not know the category name.
Yeah.
Yeah, you are right actually. Let's go back. Okay. Remember I said in the beginning, for politics, remember this circle I drew, right? Nobody knows that the name of the topic is politics. The model would have a distribution of keywords here. A
Okay.
distribution of keywords here, which seems like of type politics. Model does not know it is politics. For model, it's an abstract word. I am using this for communication. It will contain words like BJP, Congress, election, speech, and so on. When I will look at those bunch of words, I know it is a politics topic. And all the documents with those bunch of words will be grouped into this topic. Does it now making sense? Is it now making sense? So the model learns only bunch of words which are very close to each other. That's what the model learns.
I mean, how the, maybe you proceed and I understand. Okay.
How does it do it, right? That's the question.
Yes, I mean, how would a connection between the words will happen?
Yeah, that's what we will learn.
Okay.
Wait, I have a question. So does it how do we decide the number of like themes over here? Like over here, like does the model itself do it by itself, or do we give it as an input that do into like 4 separate themes?
Well, the model does not know how many topics are there, but there are some intuitions that we
Okay.
use to find out how many topics are there. And that's the purpose of hands-on demo. We will come to the hands-on stuff. There I will show you is exactly this question, right? Tanushri, that you asked. I am asking the same question in my notebook. How do I know how many topics are there? Are there 2 topics, 4 topics, 6
Yeah.
topics? Because nobody knows in the beginning how many topics are there. So this is the hardest problem actually in clustering and in topic modeling. But we will use some, intuitions. We will use some search. We will do some search there, and I will show you in the hands-on demo how to
Also,
find out.
this type of topic modeling, does it fall under what do you say? Soft and fuzzy clustering?
You can say kind of, yes. But remember, there's a difference. When you do clustering, you don't have these latent words here. There's a difference between clustering and topic modeling. Clustering is very close to topic modeling, very, very close, but little different from topic modeling. Clustering um, is it contains the exact words, whereas
Okay.
topic modeling may have some latent words. Latent is just go and search the meaning of latent on the Google. It's very difficult to communicate the meaning of that word. We all know what is latent. Latent means something which is hidden, but
Okay.
it's an abstract term. It's a one level of abstraction, right? Abstraction as in we have a group of words, but I cannot give it a name. I look at it, I know they are related to each other, those group of words. And that's why it should be a topic. But I cannot give it one name. You see what I mean?
So it's not like fully, what do you say, dependent on just frequency and goes more into semantics or meaning.
It goes into semantics of meanings, not based on frequency alone, right?
Okay. Thank you.
Okay, so now let's go to, this is an interesting example, right? So imagine I'm throwing a party and this is the house structure. Think of it like a house, okay? If I am inviting people to this party and in this house, there are 3 corners as you can see. At the first corner, I have food. At the second corner, I am streaming a movie. And on the third corner, I have music instruments. Okay? But before even I go there, if I invite people to a party, I'm thinking of it from a probability point of view now. Okay? And I want you to answer this. Where do you think people will be located in this room? And this will help you understand probability also. If I'm inviting people to a party into this house, where do you think people will be located?
Depends on the time.
Depends on the time, but even before that, right? There is nothing here, no food, no music, no movie. Where will the people located? Will they be all grouped together in one place, or option number B, they will be distributed throughout the room. Distributed throughout the room, right? I mean, each person is uh, is a free man here, right? He or she has the free will to go to any part of the any place in this room, any to any point in this room. Think of it like a XY axis, right? So, but now if there is a food, there is a movie, and there is a musical instruments to play with, what would happen? And like I said, people can be anywhere in the room in the beginning, right? These yellow dots are people. So what will happen now? At the beginning, people will go towards the food. Most of the people, let's eat first. Who knows, will there be any food left later or not? One guy who may be not very hungry would go in, and a movie buff would start watching the movie. One or two may go in and watch and play with music, right? But 2 hours into the party, you will start seeing people moving around. Well, there will be a person or two still grabbing some food, um, some people grabbing food and watching movie. This guy, basically, he eating food also and watching movie also. Some people still watching movie, playing with music, eating food, playing with music. You will see most likely this kind of pattern, right? 2 hours into the party. 5 hours into the party, what would happen? Food is, you have watched a movie, you have played with music, and you have had your food. What is most likely going to happen? What people do in parties? They socialize, and they will start making groups and talk to each other, right? So this is the kind of distribution I will have. Remember, this example I am talking about to tell you about Dirichlet distribution. Okay, this is a Dirichlet distribution. This is a Dirichlet distribution. This is the Dirichlet distribution, 5 hours into the party. Another example is at one side, a lion comes in. Let's say I'm throwing a party in a jungle. On one corner of the room, suddenly a fire, food, where they were cooking the food, there's a fire. What will people do? Well, people will again start, come together close to each other, as far as away from the lion and from the fire, right? So the three examples that you saw, all these three examples are of Dirichlet distribution. There's a parameter alpha that I can use to create these distributions. So distributions like what Suranjana was talking yesterday, beta distribution, uh, normal distribution. You must have all heard and read about the normal distribution in your high school mathematics, right? Which is like this, a normal distribution. What I am talking about here is a Dirichlet distribution. There are some problems that can be modeled not as a normal distribution, but as a Dirichlet distribution. And why Dirichlet distribution here? See here, these points are going to be my topics. Corners are my topics, right? And that's why there has to be a Dirichlet distribution, because it will be a triangular. What if there are more than 3 topics? I will have this one. This one is a tetrahedron when there are 4 topics. So purposefully I took an example of 4 topics to start with, to now tell you that when there are 4 topics, I have 4 corners, and each corner is my, in the tetrahedron, is my topic, right? And now you can say document is like people, right? So some smart guy came up and said that, hey, when you see this kind of behavior, it's a Dirichlet distribution. And what I want to do is I want to build a model to simulate Dirichlet distribution, and for that simulation we use Gibbs sampling. I'm not going to go to Gibbs sampling, but I will give you a good intuition of what LDA is doing. You can replace this with topics now, right? This is topic 1, this is topic 2, this is topic 3, and these are my documents, and I can either have all the documents in the middle, or I could have documents at the corners, or I could have documents like this, or I could have documents like this, right? But if I come to this slide again, and I ask you, no, this is for me actually. The first one, you can create this distribution with alpha equal to 1. The second one, you can create with alpha less than 1. And the third one, you can create if you give a value to alpha greater than 1, right? So I can create these distributions. Remember that I can create a distribution because I will use this information. So I want to highlight the word create. I am going to create these distributions. Any questions on this slide? Because this is the most important slide. I want to take a break here and make sure that everybody is with me up to this slide. Okay, Dibakar says good. Let's go to the next slide then. Now here, dots are my articles. Dots mean these circles. These are my articles, and vertices are topics, right? Which one would you prefer if you have to do topic modeling? If you want to do topic modeling, which one among these three?
Second one.
Yes, second one. This is a very difficult problem to solve, right? The first one. Why difficult? I don't know. Is it whether this document is science? This looks to me some science, some politics, some sports. And this one is more like politics, some sports, some science. But this one is good. I can definitely say this one is science, this one is politics, this one is politics, this one is sports. This one cannot decide 50% science, 50% sports. There could be an article, right, on sports where you are giving some scientific analogy. So there could be documents that fall into both the categories. Yeah. And that's where we have these soft hierarchical clustering and all those algorithms. This is the third one is not a very good data set to work with. They are in the middle, right? It looks like they are very generic articles. They can be sports, science, and politics. Lot of subjectivity in there. So yes, the right answer is I want to work with the data set which exhibits this kind of characteristics, or I want to create a distribution with these characteristics, right? And I'm using the word create again and again. I have a reason for it. Yeah. So for example, this one, sports, here I can say, see, there is no article which is 100% sports. There could be some angle of science in there. There could be little angle of politics in there. There could be, I'm saying, right? It may be 100% sports also. This, well, 100% if I have to show something, I would show it here on this edge. If I have to say the article is 100% science, I would show it here. The more it moves away, the less it is, about that particular category. So the middle one is about science, 45%, 50% sports, and so on. Okay. So here what I have is, I have converted my Dirichlet distribution to multinomial distribution. This figure, which I am circling now, is a Dirichlet distribution. But these boxes is the multinomial distribution for each document with respect to topics. These are my topics: science, politics, sports. So what I have done here is I have converted my documents from Dirichlet distribution of topics to multinomial distribution of topics, right? And there are transformers available that can do that conversion. Okay, these are my words: referendum, ball, galaxy, planet. These are my words. Now what I'm doing is I am converting my science topics. See, a document is a collection of words, and collection of words makes a topic. So I have to have two distribution: topic to document distribution and words to topic distribution. Right? Let me write that down. This is important. Document to topic distribution and words to topic distribution. So here what I'm doing is I'm doing topics to word distribution or word to topics distribution. In the previous slide, what I did was document to topics distribution. And this is my vocabulary. I'm assuming my documents contain only 4 words. Some documents contain referendum, planet, galaxy, ball. All these words I use to form my documents. So given these words, where will these topics fall into? Where will science go? Science will most likely go to planet and galaxy. Sports, where will sports go? Anybody? Galaxy is a team also, remember that. There is a galaxy team, like we have IPL teams, there is a galaxy team also. So where will sports go? So galaxy has 2 meanings. It can mean a planet and it can also mean sports. Yeah. So where will the topic sports go? I would say
Ball.
Sorry?
Ball.
Yeah, not exactly ball, but I would put it here because as I said, there is a team, sports team called as Galaxy. So the topic sports would be maybe 70 or maybe 70% ball and 30% Galaxy. And politics, definitely I will have a referendum, right? So 70% referendum, 10% galaxy, 10% planet, 10% ball, something like that. So here what I have done is I have converted my Dirichlet distribution to multinomial distribution. Yep. So you saw 2 distributions: document to topics and topics to words. Right? What are these dots represent? Anybody can help me? What are these dots in document to topics distribution? These are documents, right? And what are these dots?
Words.
These are topics. And it's perfectly okay to be confused. I get confused. And that's why I am summarizing this slide. What is sports, science, and politics? These are my topics. So you need to understand and digest this slide. I'm purposefully taking time for each one of you to register this in your mind. Here these vertices means topics and these circles means documents. But in this case, these vertices means words. Where are these words coming from? And this is important. One of you asked the question, how do we know what are the topics? I have a word here. That word tells me. For simplicity, I just put one word here, but there could be multiple words. Right? I could have a referendum, I could have speech, I could have here BJP, Congress, and all those kind of words. When I look at them, I say, hey, this bunch of words look to me like politics. I think it will start making sense for you now, right? Let's go to next slide.
Is there an optimal set, or can there be more?
Optimal set of?
Optimal set of topics.
No, there is no optimal set.
There's
Very,
a min or a.
actually, clustering and topic modeling, uh, there is no clear definition, not definition, there is no clear way of telling how many topics are there. It depends on the granularity. I remember 5 years ago, I was working on this. I had this bunch of uh, insurance articles and I was trying to cluster them. I produced one clustering, and to me it looked like, wow, this is good clustering. But then I used another parameter and I got very small multiple clusters. Think of it like granularity. You can, within science, you can have 5 more clusters, can't you? One for let's say chemistry, one for let's say physics, one for let's say biology. So I can have 3 clusters within science also. Am I answering your question, Parvati?
Yes. Yes.
Okay, good.
And is there a dimensionality also in addition to the, like for example, if I just take politics and I distribute it over a timeline, so that cluster itself has a whole different dimension to it. So something that happened like 50 years back may not be in context today. So if you're trying to draw an inference, then it's how do you figure out what's the better one?
So you are saying dimension. So let me try to understand your question. And this looks to me like a um, good research topic could be. So are you throwing an angle of time into the uh, uh, the document representation? So there could be 2 documents.
Right.
Both are
Separate.
talking about sports, but one is like 50 years ago and one
Right.
is now, right?
Right.
I haven't seen that anybody looking into this kind of dimension, but maybe there is something. So honestly speaking, I'm not aware of that. And that's why I said it could be a research topic also that one can start, but one has to build a motivation for it. Why would I want to have, why would I want to have um, a third dimension, right? Other than the other dimension that I already have um, on the timeline. Timeline.
This could, if you extrapolate this to some medical diagnosis, for
Oh
example.
yes. Oh yes.
Right. Yeah, and then I'm looking at a particular case history. I'm looking at it in different snapshots. Then you can make a lot of sense when you also group it in another dimension. It could be time.
Correct.
It could be the multiple symptoms.
Yeah, that's good. Yes, this could be somebody can take it up as a research problem.
So Harshit, if I can chime in,
Yeah.
there are some linguist studies which do this, where some words are kind of phasing out or becoming obsolete. So
Yeah.
they take that time dimension also into factor and see with time what new words are coming in, right?
Correct.
With time, also if you want to see, let's say in the domain of biology, you want to see earlier what were the key areas in biology that people were more focused on. And now with time, there are new areas coming in and some areas are getting obsolete, maybe because, we are already at the state of the art, maybe, right? So probably
there is.
yeah.
Yes. Now come to think of it, Google, you can go to Google and you see how the new topics are emerging, right?
Yes.
So Google has this topic chart, topic distribution thing. But I think Parvati has a different point. Parvati is saying use that dimension during topic modeling or during clustering.
Right. Yeah.
Right.
Yeah. Nobody, I don't think so. People have used the dimension of time as a dimension for
Clustering.
I don't remember. I spent a lot of time during my PhD when I was for months and months I was doing clustering. Things, keep happening, right? So maybe in the last 10, 12 years, there may be people who have done some work, but this is a good idea, Parvati, right? Somebody should pursue that. Okay, let's move ahead. So Now coming to little bit mathematical, so please bear with me and I will try to make it as easy as possible and as intuitive as possible. What I want by the end of this whole set of slides, you to get the intuition of what Dirichlet distribution is and what latent Dirichlet analysis is. I have only two objectives for today. Okay, so I have a machine here and that machine is generating documents. Remember I said creating documents. I said creating. I kept saying creating, creating, creating. There are two types of algorithms in machine learning, generative and discriminative. This one is generative algorithm. And that gets a little, it's not very intuitive to think about why am I generating documents now? But we are actually generating, and I will tell you how we do that. So I have a machine. What this machine does is it uses, it learns or creates topics to terms distribution, Dirichlet one, and the multinomial one. And there is another knob in my machine that learns or creates topics to document distribution. See, I have the documents and I have the terms, right? These things are given to me. Documents are given to me. Terms are given to me. Each document contains terms, right? So what I do is I learn these two you can think of them like my knobs, right? I can control these knobs to create topics from document terms, right? Uh, and I'm learning a distribution and creating documents from that distribution. Two sentences I'm saying. Learning a distribution, creating documents from that distribution. Okay, remember that. Learning a distribution, creating document from that distribution. So I generate document one. And now I say, I have generated this document one. Is it similar to any of my documents in all the documents that I have? It may be, it may not be, right? And I check, how much similar is it? And then I have another machine where I change these distributions, right? Same thing, topics versus terms distribution, topics versus document distribution. But I can control my alpha parameter. Remember I told you about the alpha parameter that I can, play around with to create different Dirichlet distributions of topics to terms, topics to document. So I play around with that alpha and I have, for the same machine, I generate document 2 and I compare how similar is it to my actual document. One of them will be doing good than the other. The one machine which is doing good is the machine I'm going to use for topic modeling. I want to just take a pause here for a minute or 10 seconds to wait if anyone has a question.
Divakar here.
Yeah, Deepak.
Is it something similar to generative adversarial network kind of?
No, this is not adversarial network. Adversarial networks are like you are you create adverse you generate adverse information to teach your model how to uh, do the prediction in adversities. This is not adversities we are creating.
Okay.
These are not GANs, but these are generational. Machine learning algorithms have been traditionally generative versus predictive. These ones are generative class of algorithm, LDA. Yeah.
Thank you.
Clustering is not generative. Remember that. Clustering is predictive. Topic modeling is generative. That's one lower level difference, you can say between these two algorithms. Basically, I want to make a machine. That machine has two components. One component create topics for the terms and one create document for those topics. It's creation. And then I see of all the documents I create, how similar are those documents that the machine create with the actual documents? How similar are those documents? That's what I want this machine to learn. And the closer it gets to my actual documents, those parameters I use for my topics. If no questions, I will move to the next slide. 3, 2, 1. Okay, next slide. So as I said, I create multiple machines. Each machine will have different value of alpha for to tune these two, right? And there are other parameters also. So this one is another parameter, but these are the two essential parameters. And I want to select the machine which does the best. And let's say this is the machine. So this is the machine that I will use for my topic modeling. Okay, 5 minutes, the difficult stuff here. So this is the mathematical modeling of the probability of generating a document. And there are 4 components. And if you have been listening to me very carefully for the last 4-5 slides, I will relate them with this mathematical equation. The first one is a Dirichlet distribution of topics with respect to documents. So what I do is I pick a random point, right? And I want to generate a document here. I want to generate a document here. And then for this document, what I do is I now, because this is most likely science, less politics and more sports, right? So what I will do is I will have words related to science in my documents, 70% of the words related to science, some words related to politics, and some words related to sports, which I can get from this distribution. And then I will have my topic to words distribution, right? For each of these topics, I will generate words, right? Which I have from this Dirichlet distribution. And now when I have topic to words distribution from the third one, the fourth one I use to generate the words. It's a generation. I am generating a document. And when I generate the words, I get this document, the probability of generating a document, right? So this mathematical formulation I use for generating a document. And this is the machine that we have been looking at with those knobs, but that's actually the machine. It looks very similar. Alpha and beta are my parameters, Dirichlet parameters, right? Alpha and beta. One for topic to word distribution and one for document topic distribution. Sorry, right? So alpha I use for Dirichlet distribution of topics over document. Beta I use for Dirichlet distribution of topic over words. And then I convert from Dirichlet to multinomial distribution for picking topics for the documents, right? And then then I convert the Dirichlet distribution topic over words to multinomial distribution for picking words. Remember those two triangles I was showing, right? This is what these alpha, beta, theta, and phi are doing. And then once I have these multinomial distribution, I can start generating document. Okay, I should stop here for a moment, and I know I went a little faster over these things, but I will be happy if anyone wants to ask questions on this. There's a very strong correlation between this slide, and now I should say between this slide and between slide number this one, slide number 18 and slide number 22. They're very closely related. So I want to stop here and would like to take questions for 2 minutes. And then we will go to the hands-on, Python notebook.
How is the comparison made between the generated document and the actual document?
Divakar, your voice is breaking. Can you please say that again?
How is the comparison made between the generated document and the actual document?
We just compare two documents, right? The one that the machine generates, and then we do a similarity over all the documents.
Kind of precise similarity?
You can say cosine similarity, yes.
Okay.
Okay. So this is the pipeline we are going to see in the Python notebook. I will start from a bunch of, and please, this is important, okay? Make sure that you register this in your mind because Python notebook is very long. And this is what it is happening in that Python notebook. I have a bunch of documents. In fact, in the notebook, I will have 1,000 documents. Okay, I will have 1,000 documents. And from those 1,000 documents, I will do pre-processing. Remember yesterday what Debanjana told about pre-processing, stop word removal, stemming, unigram, bigram, and then I will create a vector space from it. Vector space is what? It's a bag of words model, right? We create a vector for each document. We take each document and represent it as a vector over the vocabulary. So one vector would be like this, a vector of real numbers. High school, right? High school mathematics. A vector of real number, right? This is my document D1. And what are these features here? Can anyone tell me? What are the features of this vector? Let's say I have D dimensions and I'm using a vector space model. What does all these represent?
Teachers, it's students are trying.
Sorry?
No, sorry.
Can you please say that again? The features
No,
are?
there was some noise. There was some noise. No idea yet.
Okay, Nidish is saying topics. No, I'm not talking about topic modeling right now. Okay, I'm asking about a very basic question. I'm doing vector space modeling. I have a document D1. We know that we create a vector and it's a real vector. And this was told to you yesterday. What does these features represent in a bag of words vector space model? And this is important to know actually. Okay, I can give you options.
Vectors of words?
Yes, it's a vector of words. But which words? Let's say I have 3 documents, D1, D2, D3. And in D1, I have 10 unique words. In D2, I have 20 words. In D3, I have 5 words. Okay? And from these 3, I get unique words. I'm saying unique now, right? There may be words repeating among them, but unique words are 15, say for example. Okay? Then D1, this part, how many words does it represent? This whole vector.
15.
Good. This is 15. Very good. But in this vector, there will be how many zeros? There will be some features which will have a 0 in them. How many will have 0 in them?
5.
5 of them. Good. I think everybody knows. Then let's go to the hands-on demo. That's perfect. Any questions on this?
Harshit, hello.
Yes.
Can you
Yes,
hear?
yes.
Yeah, I
can.
could understand till here, but can you talk a little bit about the validation of the clustering also? So after we cluster it,
yes,
either by the mainly different methods you said in the introduction. So any method when we are using the clustering, how do I validate? So each method will have different hyperparameters to optimize. So
Correct.
which criteria we are using, which dimension, how many dimensions we are using, and there may be different. So for example, in k-means, you have to choose the number of k and all. So there will be different hyperparameters, but at the end, how will I validate how will I validate the final clusters?
Correct. So there are lots of um, algorithms or metrics, I should say, not algorithm, right? And that we use for, see, the problem is, right, there is no way of validating it
Yes,
because you don't
because
have the ground truth,
yes,
right?
yes,
You don't
yes,
know.
yes.
Good. So what we use is these, I preferably like these three metrics. One is purity, one is entropy, one is Silhouette coefficient. If you remember from your um, introduction to information theory, entropy, what is entropy? Can anyone tell me what is entropy?
Measure of randomness.
Randomness. Yes. What do you think good cluster should have? More randomness or less randomness? A good cluster or good topic. Should there be some
Less
random
random.
less randomness? So here you go. If you have if you have good topical clusters, your entropy should be
Lesser.
low. If you have high entropy, most likely your clusters are not good. Purity. I like entropy actually the most. But let's go to purity also. It's a very popular metric, purity. What is purity means? Purity means one cluster should have all the documents of the same type, very close to each other. High cohesiveness is the purity. How do we measure that? Let's say I have a cluster, okay, and I have three documents in them. Let's call them as D1, D2, D3. Okay? Versus I have another cluster which contains, let's say again, another three documents, call them as D1 dash, D2 dash, and D3 dash. If I compute similarity between D1, D3, D1, D2, and D2, D3, I can have three similarity values, similarity scores. I add them, I take the average, I get a number of 0.9. Okay? I do the same thing here and I get a value of 0.3. Similarity between these, right? Average similarity. Which one do you think is representing more cohesive documents together? The first one or the second one?
I think it's first one.
It's the first one, right? High similarity, not the distance. I'm using similarity. Some algorithms use distance also, which is inverse of similarity. I have a pure cluster. They are so similar to each other. Okay? That's the second metric. The third one, which I love the most, is the Silhouette coefficient. It is the ratio of cohesiveness to separability. Remember, purity was only calculating this thing. Now, what does this mean? Cohesive to separability? Separable, right? It is saying that a good cluster should be cohesive and far away from other clusters. This is what it is trying to measure, which makes sense, right? I should have good clusters like this, one cluster here, one cluster here, one cluster here. They should not overlap. If they overlap, then separability will have a low value. Sorry, will have a high value and your ratio will be small. So there are three such metrics for computing there are many more. There are not three. There are like tens of them. There's a whole, I remember had to have read through a thesis on the evaluation metrics for clustering and for topic modeling. Yeah. But these three are, I would say, are very likely going to be used. Yes. So Rajeshwari, have I answered
Thank
your
you.
question? Yeah.
Yeah,
Okay.
yeah,
Good.
thanks. Thank you.
Okay. So now let's go to the notebook. Right. Is it? So I have here two notebooks. Both of them are the same. The the first one I created and it shows all the outputs.
Actually, one moment before I thought remember that command which is told to execute.
I cannot hear you. I cannot make out what you're trying
Initially,
to
you
say.
showed one command to be executed.
Oh yes, yes, yes.
Can you show me again? I thought it.
Where is that command? This one. It's on the GitHub
Okay.
page. I can even, but you have to make sure that you are in the environment tutorial, and from the terminal you execute the command. Right? Like for example, I would go to now when I am in the tutorial environment, I would take this command and I would just run it here, right? I won't do that right now because I've already done it. So, but I suggest you to do it, right? Otherwise, there is a step in the notebook where things won't work, right? It will throw an error. And I can tell you which step is that. That is cell number. Hold on. This one, right? Cell number 20. Here you will see that this cell may not run if you have not run this command. Okay. So let's go back to the notebook. Any questions before I begin? So here I am using several libraries. Some of them are generic libraries, for example, collections. This is to create a distribution. Um, Gensim is the one that I am using for topic modeling. Spacey for text processing and JSON for reading JSON files. Pandas, as yesterday uh, Debanjana told you, is one of the very useful libraries, packages to model your data as a data frame, as a table, right? And matplotlib for the graph. Logging I'm using to collect the logs in a file, gensim.log, so I can go back and debug and not pollute my terminal, my notebook. PyLDavis. This one I'm using for visualizing the output of LDA topics, basically, right? And we will see that. Word cloud, you know what is word cloud, right? For visualizing the um, words um, in my documents, right? Okay. Um, and this one, Bokeh. Bokeh is a very good library. This allows you to make a graph, an interactive graph. You can interact with the graph. I love this Bokeh package, which I have used here. Um, and NLTK is all for processing your documents, stop words, unigram, bigram, and all that stuff. Okay, let's go here. Let's get a little adventurous and run it. So, um, yeah, it's running. It will run, I know. Uh, I am using this URL. You can run the second one, and this is a uh, consumer complaints data set from the finance side. right? And I am taking the tail, last 1,000. Some of you can say, uh, head 1,000. I am taking the bottom 1,000 ones, but try with head 1,000. Take first 1,000 complaints. I am taking the last 1,000 complaints for this um, one, right? For this hands-on demo. So it will read the data, create a data frame. The name of data frame is df all. It contains all the records. I create a small data frame and I print the first 3 records, right? When I print the first 3 records, remember here I said column width equal to 400. So now I can see 400 words. That's why I'm seeing these 400 words. So it says that this is the column, consumer complaint narrative. Credit reporting agency refused to remove information. So these are the complaints. I noticed accounts on my report that did not belong to me. I immediately sent in a dispute to blah, 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 blah. Didn't hear back. So I sent on letters again for a demand for a comply some date. Today is this date, and it is sad I still haven't even heard back from these companies yet. So this is a kind of a consumer complaint on the finance side. But let's look at some visualization. So what is the DF product? What is the product? So each complaint has been grouped into some products. Credit reporting, credit repair services, consumer reports. So these are the products, right? Debt collection. So how many such products are there? Debt collection, mortgage, credit card or prepaid card, checking or saving account, and so vehicle loan, student loan. Most of the complaints are from credit reporting or credit repair services. Right? Of all the complaints, approximately 50% of them, there are total 1,000 complaints, 500 of them are from the credit reporting. And then I also want to know the distribution of issues here, right? So these are the issues. And then which companies are getting the most number of, complaints. So how do I view this one? I right click, I goes into a new tab, and then I can expand it. Equifax gets the most number of complaints. So there are 2 companies that get most number of complaints, Equifax and TransUnion, Experian Information, Capital One, and so on, right? Lots of companies in this data set. And then I want to look at which states, um, if you see in the data set, there is a column called as state. LA, TN, Tennessee, LA, and so on, right? So I want to see here which state the complaints are coming from. So you can look at it later. Let's go on. So as I said earlier, the consumer complaints are under the column consumer complaint narrative. So I create a data set of all the complaints, and I am printing one of them here. Open a fraudulent case with Bank of America. After sitting on it for 3 months, blah, 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 did some paperwork, same thing, right? What I was reading earlier. I'm doing some pre-processing here. What pre-processing am I doing? I am removing emails, removing new line characters, removing single quotes, and removing those excess, like these ones, right? Like these ones. So after I remove them, this is what I get. Open fraudulent case with Bank of America, and after sitting on it. So now I have a bunch of tokens for each complaint. Okay. I'm just showing the first complaint as a bunch of tokens. What I want to do is I want to remove stop words from it and create unigrams and bigrams. This is what I'm doing in this cell. If you see the output, now I don't have any stop words here. The words like and, to are gone, right? Open, fraudulent case, set, month, decide, change. Yeah. And now I create my dictionary. Remember in the PPT, the last slide I was saying, what does the vector looks like? It's a dictionary, right? The whole dictionary, the whole vocabulary. So I create a dictionary and then I convert it to bag of words, a vector. Now each document looks like this. What does this mean? The word 0 has frequency 1. The word 1 has frequency 1. The word 2 has frequency 1. What is word 0? Word 0 is address. How do I know word 0 is address? It's in my dictionary. So I have to use my dictionary to find the index of word 0, which is address. Word 1 is case. So basically I just make a vector, real vector like this, with zeros and ones. The frequency 1, 1, 2, 1, 1, 1, 1, 1, and so on. Okay, so this is my vector. This is my bag of words vector. So I will have two approaches, one using bag of words, one using TF-IDF. And now I just print it. Okay, what I want to do is I want to look at the word cloud. Okay, so for that I take my data and I combine all the complaints, all 1,000 of them into one sentence, which is long text. I don't want to print it here. It's huge, right? And then I want to visualize what are the important words in the consumer complaints. What are those words? These are the words: information, account, report, payment, credit, request, loan, company, and so on, right? The size is based on frequency. Can I make it bigger? Just curious. No, I can't. Okay. And then I want to study the word distribution. Basically, I want to see which words are more prominent. When I saw that here also, account, information, but now through a bar graph. Okay. Account, report, information, payment, credit, request, call. And now the golden question: how many topics are there? Oh, no, nobody knows that. So let me start with a random number. When I start with a random number 4 and I create my LDA model, and I'm saying here run it 10 times, each time do 100 iterations, right? What it learns is these 4 topics. Now here I told you a topic is not a keyword. It's a bunch of words: account, payment, report, credit, request, validation, consumer. This is one topic. This is second topic: account, information, report. This is a dispute. Some dispute, right? On credit. This one is a legal right, account, validation, that kind of topic. Topics are not keywords like we think. Politics, that we use for teaching when we want to convey something. But this is how a topic looks like. These are the 4 topics. A topic is a distribution of words. This is a distribution of words. Is it making sense for you now? When I was telling you over there, a topic is a collection of words. So now I have this model, which I'm saying LDA model, bag of words, 4 topics, and these are the 4 topics. I want to now see what is the coherence of those topics. I get a 32% coherence. Is it the best coherence? I don't know. But let's visualize the topic clusters. I use this PyLDavis library. It is showing me the 4 clusters. This is cluster number 1. And this is from the bouquets, right? Remember I told you, gives you interactive visualization. Now when you look at topic number 1, these are the words on the right side. These are all the words in topic 1, right? And this is topic 2, all the words in topic 2. these are the words in topic 3. And these are the words in topic 4. But look at topic 4 now. It has loan, call, credit, time, payment. Whereas topic number 3 is less of account, less of payment. Why I'm saying less compared to 1? Account is so high, 1000 words of type account, right? This is topic number 3. But what do you think? Do I have the best topics or can I do better? Any ideas when you look at this graph?
Like the biggest one is overlapping with another topic.
Yeah, they should
Why would you
actually
want
be,
that?
yeah, they should be into one topic, right?
Yeah.
Yeah, if I were, I would run this again and say number of topics equal to 3. Here I will go and say number of topics equal to 3 and run it again. And then I will see what happens. Right? So I want you guys to try these things later on, right? I'm purposefully not doing it right now. But this is just an intuition. Right? What I can also do, I can visualize my documents to topics. So this is using, what it is doing is, it is giving me a visualization of the topics that I have discovered and how does documents and topic distribution. It is showing me that. So there are 4 topics and these are documents in topic 1. This is topic 2. Sorry. Topic 3 and topic 4. Okay. So I can get a distribution of topics to documents and I can know topics to words distribution also. And I had document to topics distribution too here, right? Here. So all the 3 distributions I can actually look at and get the feeling of how my clustering is coming along. In my opinion, this should be one topic. There should be still 4 based on this, right? But is there a way to identify best coherent clusters? Well, I can do is this. I can write a for loop. I can start from number of topics 2. I can say maximum go to 40 and step is, in steps of 2. So what I'm here doing is I'm calling this function compute coherence values and I start from 2 topics, go all the way up to 42 in steps of 2 and I check how much is the coherence. So when number of topics are 2, my coherence is 31. Number of topics are 4, my coherence is 32. Number of topics are 6, coherence is 35 and so on. When I look at this, I find that when number of topics are 8, I get the best coherence, 0.36. Or maybe when it is 12, 0.3596. They're pretty close. So what I do is I go ahead and I visualize my this thing. And I see here at topic at this point I get a best coherence, right? So I want to visualize with topic clusters 8. So I take the model list and I want to now visualize it. Yeah. By the way, this model contains all the 20 models, all of these models, right? Model list bow. It contains all the 20 models. The first one is topics 2. The second one is topic 4. The third one is topic 6. The fourth one is topic 8. So in this one, I am looking at topics 8, the third one, right? I said model list topic 3. These are my 8 topics. I don't think 8 is good, but my model says this is good. This is the best, actually, according to my model. There is some overlap. 2 and 4 should come together, in my opinion. 1 and 5, some overlap. 8 is a different topic. You see now the problem. It looks to me reasonable. 7 and 3 are far away from 1, and I can say this is one big topic. I can free to choose that. But then it depends what granularity I want. Now I will go do the TF-IDF representation. So I convert my corpus into TF-IDF And here I have the, remember earlier I was having ones and zeros. Now I have TF IDF scores here. So each vector looks like this, a vector of these real values, right? And then I train the LDA model, but this time I'm purposefully saying 2, because when I looked at this, I got a feeling there should be 2 topics, topic 1 and topic 2. So now I am training with number of topics equal to 2, but now I am using a different library, LDA multi-core. Earlier I was using uh, LDA model. The difference between LDA model and LDA multi-core is there is a word core here. Well, core means it is faster, right? It can use multiple CPUs. So this one is faster than the previous one. So when I run this one with 2, I get a score of 0.35, coherent score. And when I visualize it, I do get these 2 topics, right? Very well separated. But is this the best topic modeling am I doing? I still don't know. So let me now again run it for, uh, 20 iterations, and I can look at where do I get the best topics? Well, from here it appears I get the best topics at this one. This is topics 22, which means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Model number 10. So model list TF-IDF 10 should contain the best model, right? Which has the highest coherence. And this is the visualization, right? This is the model number 10. So I look at those 10 topics. Again, it's a distribution of words: consumer, reporte, validation, information, section, and so on. So there are these 10 topics here, right? And now I visualize, sorry, 22 topics. Index is 10. Look at this beautiful graph. All those should come together. So there should be, I'm fairly convinced, even though coherence is saying there should be 22, but I think this is the best one, 0.36. Consistently, I am seeing 2 or 3 topics is what there should be. So I would go ahead and train another model with 3 topics, right? So this is how we do the evaluation. These are more intuition based. These are more hit and trial based, right? You have to work with the experiments multiple times to actually be able to come out with good topics that you can use for your final model. Yeah, I will stop here, and I hope you find this session useful, and I hope this notebook will give you enough uh, room to play around with. Yeah.
One question. Hello?
Yes, I'm listening. Go on.
Yeah. So suppose you in the last one, just the one below. Yeah, this one. So if we take out, if we just remove the data for cluster 1 and 2 and concentrate on this small thing, can we do some kind of hierarchical way also to find out whether there are still subtopics in that?
Yes, I mean, we can remove this, all the documents from 1, all the documents from 2, and you are saying just work on these documents. Yeah, we can do that. Yes.
Okay.
You have to write some piece of code for it, by the way. Yeah, it's not. Maybe you need 3-4 lines of code. Am I missing any questions that were on the chat window?
No, it should be a good.
Okay, then I should stop here and give the control back to Patiti.
Yeah, thanks, Harshit. Great session. So let's take a 5 to 7 minutes break. Let's come back 11:20. Thank you.